Every time astronomers measure how far the universe extends, every time they think they have finally reached the edge, the same thing happens. They discover that they have not seen anything at all. They have seen a fragment, a keyhole, a grain of sand pulled from a beach they will never finish walking. Consider the single photon that, as you read this sentence, is striking a detector in a quiet laboratory somewhere on Earth. That photon began its journey through space when our planet did not exist, when our star did not exist, when the atoms that would eventually make up your body were still scattered across other dying stars and galaxies that have since faded into the cosmic web. The photon traveled for billions of years through expanding space, redshifted into invisibility, then arrived at a piece of glass cooled to near absolute zero, and was recorded as a single point of data. We pointed our telescope at what looked like nothing. We waited, and the universe answered. But the answer it gave us was not the one we expected. Tonight we are going to ask a question that sounds simple and turns out to be the most terrifying question in physics. How big is the universe really? Not how big does it look. Not how big is the part we can see. How big is the whole thing? And the answer, when you follow the evidence honestly, will not give you comfort. It will give you vertigo. It will give you a quiet ache somewhere behind your eyes that comes from your brain trying to picture something it was never built to picture. We are going to start small. We are going to start with the ground under your feet. And then we are going to climb step by step, layer by layer, scale by scale, until the numbers stop making sense. And then we are going to keep climbing. Because the truth about the size of the universe is not just that it is large. The truth is that the universe is structured in such a way that no matter how powerful our instruments become, we will never see most of it. There are regions of space already permanently closed off to us. There are galaxies whose light has been racing toward Earth for the entire age of our solar system, and will still never arrive. And beyond all of that, beyond the edge of what light can ever reach, there may be a universe so much larger than our observable bubble that calling our bubble a fraction of it is generous. By the end of tonight, you are going to look up at the night sky and understand for the first time that what you are seeing is not the universe. It is a single page torn from an encyclopedia of pages we will never read. If you enjoy these nighttime journeys through cosmology and the deep questions science is just beginning to confront, take a moment to like the video and subscribe to Hidden Beyond Stars. It genuinely helps us keep making documentaries like this one. Settle in, we are going to walk to the edge of everything together. And we are going to find out that the edge is not where you think it is. Let us begin with something familiar. The Earth. You are standing on a sphere of rock and iron, approximately 12,742 kilometers in diameter. That number sounds large. It is not. A commercial airliner traveling at cruising speed could circle the planet in about 40 hours. Light, the fastest thing in the universe, makes the same trip in roughly 0.13 seconds. To light, the Earth is barely a heartbeat across, and the Earth is the largest thing you have ever directly experienced. Now, lift your eyes. The moon hangs in the sky. It is the closest celestial body to us. It looks close. It feels close. Poets have written about it for 10,000 years as if it were a neighbor leaning on a fence. It is not a neighbor. It is 400 kilometers away. You could line up 30 Earths between us and the moon and still have room left over. Light takes 1.3 seconds to make the journey one way. A rocket launched at escape velocity needs about 3 days. The Apollo astronauts who walked on its surface in 1969 traveled farther from home than any human has been before or since. And the moon is still the first step, still the doorway, still the curb at the end of our cosmic driveway. Now widen your view. The sun, the star that anchors everything you have ever known, sits 150 million kilometers away. That distance has a name. We call it 1 astronomical unit. It is the standard yardstick we use to measure our solar system. Light from the sun takes 8 minutes and 20 seconds to reach your eyes. The sunlight warming your skin right now left the surface of the sun while you were doing something else, something that already feels like yesterday. The sun itself is a yellow dwarf, an utterly average star, one of an estimated 400 billion stars in our galaxy. Its diameter is about 1.4 million kilometers, large enough to swallow 1 million Earths with room to spare. And the Sun, this furnace at the center of everything we depend on for life, is one of the smaller stars out there. The largest known stars, hypergiants like UY Scuti or Stephenson 218, have diameters more than 2,000 times the Sun. If you placed Stephenson 218 where our Sun is, it would swallow Saturn. Its outer edge would brush against the orbit of Uranus. Our entire inner solar system, all the rocky worlds and asteroids and the warm bubble we call home, would be inside that star with thousands of astronomical units to spare. And Stephenson 218 is not the largest star in the universe. It is simply the largest one we have happened to detect so far. Hold that thought, because there is something important hiding inside it. The universe does not show you everything. It shows you what your instruments can see. Now keep widening. Beyond the Sun lies the rest of our solar system. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, the gas giant that may have saved life on Earth by hoovering up comets that might otherwise have struck us, Saturn, with its rings of ice and dust, Uranus and Neptune, the two ice giants spinning silently in the dark. And then beyond Neptune, the Kuiper Belt, a flat ring of icy debris that contains Pluto and millions of other frozen worlds. Beyond the Kuiper Belt lies something most people have never heard of: the heliopause. This is the boundary where the solar wind, the constant stream of charged particles flowing outward from the Sun, becomes too weak to push back against the gas and dust of interstellar space. Past the heliopause, you have technically left the Sun's influence. You are in the spaces between the stars. Two human-made objects have crossed this boundary: Voyager 1 and Voyager 2. Voyager 1 crossed in 2012. Voyager 2 crossed in 2018. They are the farthest human creations in existence. And they are still, by any meaningful measure, in our cosmic front yard. Voyager 1 has been traveling since 1977. As of now, it is approximately 24 billion kilometers from Earth. Its radio signals, traveling at the speed of light, take more than 22 hours to reach us. When NASA sends a command, they wait nearly a full day for confirmation that the spacecraft received it. And here is the part that should disturb you. Voyager 1 has not even reached the inner boundary of the Oort cloud. The Oort cloud is a vast spherical shell of icy bodies surrounding our entire solar system, believed to extend from roughly 2,000 astronomical units out to perhaps 100,000 astronomical units from the Sun. It is the deep freezer where long-period comets originate. It is the outer suburb of our star's gravitational influence. And Voyager 1, traveling at 61,000 kilometers per hour, will not reach the inner edge of the Oort cloud for another 300 years. It will not pass through to the far side for roughly 30,000 years. Let that settle. 30,000 years from now, longer than the entire span of recorded human history, longer than the time between the cave paintings at Lascaux and the smartphone in your pocket, Voyager 1 will still just be exiting the Sun's gravitational neighborhood. It will not have come close to another star. It will not have even started the real journey. And the nearest other star, Proxima Centauri, is 4.24 light-years away. At Voyager 1's current speed, the trip would take more than 73,000 years. We have built spacecraft that can leave Earth. We have not built one that can meaningfully cross the gap to even the closest star. The gap is simply too large. And that is the next layer of scale, the space between stars. Most people, when they imagine a galaxy, picture a glittering pinwheel where stars are packed shoulder to shoulder, brushing against each other, lighting up the night in every direction. That is not what a galaxy looks like. That is what a postage stamp of a galaxy looks like when an artist needs to fit it into a frame. The real geometry is something else entirely. Imagine shrinking the Sun down to the size of a single grain of sand, 1 millimeter across. On that scale, the Earth would be a microscopic speck about 12 centimeters from the grain. The entire solar system out to Neptune would fit comfortably inside a small room. And the nearest star, Proxima Centauri, that other grain of sand, would be roughly 30 kilometers away. 2 grains of sand, 30 kilometers of empty space between them. That is the density of a typical region of our galaxy. Stars are not packed together, they are scattered across vast oceans of vacuum. The Milky Way is mostly empty. The night sky is mostly empty. Everywhere you look, the universe is mostly empty. And our galaxy, that mostly empty pinwheel of 400 billion stars, is 100,000 light-years across. 100,000 light-years. A single light-year is about 9.5 trillion kilometers. The distance light travels in 1 year of unbroken flight. Multiply that by 100,000. That is the diameter of the Milky Way. And we sit inside it, on a minor arm called the Orion Spur, roughly 26,000 light-years from the galactic center. We are not in the center, we are not at the edge, we are in the suburbs. From our position, when we look up at the band of light we call the Milky Way crossing the night sky, we are looking edge-on into the disk of our own galaxy. We are seeing the collective glow of billions of stars, most of them too far away to resolve as individual points. And that band stretches across the entire celestial sphere because we are inside it. We are surrounded by it on all sides. We are immersed in our galaxy the way a single fish is immersed in an ocean. Our solar system completes one orbit around the galactic center every 230 million years. The last time we were at this position in our orbit, dinosaurs had not yet evolved. The next time we return, the human species will almost certainly no longer exist. The galaxy operates on timescales that mock us. And it is just one galaxy. Until just over a century ago, humanity did not even know that other galaxies existed. In 1920, two astronomers stood in front of an audience at the Smithsonian Museum of Natural History and argued about the size of the universe. Harlow Shapley insisted that the Milky Way was the entire universe. Every fuzzy patch of light visible through a telescope was a gas cloud within our own galaxy. Heber Curtis disagreed. He believed that at least some of those fuzzy patches were separate galaxies, island universes, drifting in oceans of darkness far beyond our own. The debate could not be settled with the instruments available. Both sides made strong arguments. Both sides could be defended with the evidence in hand. And then in 1924, Edwin Hubble pointed the 100-inch telescope on Mount Wilson at one of those fuzzy patches, the Andromeda Nebula. He searched for a particular type of pulsating star called a Cepheid variable. These stars pulse at rates directly related to their intrinsic brightness. Measure the pulse. Calculate the true luminosity. Compare to what you observe. Calculate the distance. Hubble found Cepheids in Andromeda. He measured them. He did the math. And the math said that Andromeda was nearly 1 million light-years away. Far too distant to be inside the Milky Way. Andromeda was not a cloud. It was a galaxy. A separate galaxy. Later refinements pushed the distance to roughly 2.5 million light-years. And in that single observation, the universe was no longer the Milky Way. The universe became something so much larger that humanity had to spend the next 100 years catching up to the implication. Because if Andromeda was a separate galaxy, then those other fuzzy patches were probably galaxies too. And there were a lot of fuzzy patches. Telescopes got better. Surveys got deeper. The fuzzy patches multiplied. In 1995, the Hubble Space Telescope, named after the man who had broken open the universe, performed an experiment that should have failed. The astronomers in charge pointed Hubble at an empty patch of sky, a region near the handle of the Big Dipper that contained no known stars, no known galaxies, nothing at all visible to the most powerful instruments of the time. The patch was so small that you could cover it with a grain of sand held at arm's length. They stared at that patch for 10 days. They gathered every single photon that arrived. They processed the data. And what came back was not nothing, it was thousands of galaxies. 3,000 of them packed into a region of sky the size of a grain of sand. Spirals. Ellipticals. Irregulars. Galaxies colliding. Galaxies in their infancy. Galaxies billions of light-years away, whose light had been traveling toward us since before our planet existed. They called it the Hubble Deep Field. And then they did it again. They pointed at a different empty patch. Same result. Galaxies everywhere. And again, every dark patch of sky, when stared at long enough, revealed itself to be packed with galaxies. The universe was not mostly empty in the way we had thought. It was full of galaxies just so far apart and so faint that we had not known they were there. Current estimates place the number of galaxies in the observable universe at approximately 2 trillion. 2,000 billion galaxies, each one containing on average 100 billion stars. The total number of stars in the observable universe is somewhere around 10 to the power of 24. A 1 followed by 24 zeros. More stars than grains of sand on every beach on Earth combined. And that number, that staggering, mind-cracking number, refers only to the universe we can see. It refers only to the observable universe. There is a distinction that almost no one understands, and that distinction is the heart of everything we are going to explore tonight. The universe and the observable universe are not the same thing. They are not even close to the same thing. The observable universe is a sphere centered on you, on your eyes, on the photons reaching your detectors. It has a radius of approximately 46.5 billion light-years in every direction. Its full diameter is about 93 billion light-years. That is the part of the universe from which light has had time to reach us since the Big Bang. Anything beyond that boundary is not visible. Not because our telescopes are too weak, but because the light has not arrived. Even at the speed of light, the maximum velocity in physics, photons from regions beyond 46.5 billion light-years away have not yet had enough time to travel to us. And here is the strange part. The universe is only 13.8 billion years old. So how can we see things 46.5 billion light-years away? How can the radius of the observable universe be more than 3 times its age in light-years? The answer is that space itself has been expanding the entire time. When a distant galaxy emitted the light we are seeing now, that galaxy was much closer to us. As the light traveled toward us, the space between us was stretching, carrying the galaxy farther and farther away. By the time the light arrived, the galaxy was no longer 13 billion light-years from us. It was 46 billion light-years from us. The light came from where the galaxy used to be. The galaxy itself is far beyond that point now, racing away from us at speeds that, if measured as the rate at which the space between us is expanding, exceed the speed of light. This does not violate relativity. Relativity says nothing can travel through space faster than light. It says nothing about how fast space itself can expand. Space is the medium. Space can stretch as fast as it wants. And it has been stretching ever since the Big Bang. Galaxies are not flying through space. Space is flowing between them. The result is that the observable universe, the part of reality we can in principle see, is 93 billion light-years across. But the entire universe, the thing that contains the observable universe as one small region, is much larger. How much larger? That is where things get uncomfortable. Measurements of the curvature of space from the cosmic microwave background tell us that the universe is flat to within a margin of error of less than 0.5%. A flat universe is mathematically required to be very large compared to the observable region. Conservative analyses suggest that the full universe must be at least 250 times larger by volume than the part we can see. That estimate is the floor. It is the smallest the universe can be while remaining consistent with the data. The ceiling is harder to pin down. Inflationary cosmology, the theory that the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang, predicts that the true universe is vastly larger. Some inflationary models put the true size of the universe at 10 to the 23rd times the observable universe. Some make it infinite, literally infinite, extending without end in every direction. There is no way with current technology to distinguish between these possibilities. The observable universe is the only universe we will ever be able to measure directly. Everything else is theory, mathematics, inference. But the inference is overwhelming. The visible universe is a tiny patch of something far larger. Imagine standing inside a single room and being told that this room is not just a room. It is a single grain of sand on a beach. And the beach extends to a horizon you cannot see. And beyond that horizon there is an ocean. And beyond that ocean there are continents. And beyond those continents there are entire worlds. And you will never leave the room. You will never walk to the door. The door does not exist for you. The light from the rest of the universe has not had time to arrive. And because the universe is still expanding, most of it never will. There is a boundary called the cosmic event horizon. It is different from the edge of the observable universe. The observable universe defines what light has reached us up to now. The cosmic event horizon defines what light will ever reach us. And because the expansion of space is accelerating, driven by something we call dark energy, that horizon is closing in. Galaxies that are visible to us today, whose ancient light still reaches our telescopes, are being carried away from us so quickly that the light they are emitting right now will never arrive. The space between us is expanding faster than the photons can cross it. They are running on a treadmill that accelerates faster than they can run. They fall behind. Over billions of years, those galaxies will redshift into invisibility. Their light will stretch to longer and longer wavelengths until it falls below the detection threshold of any conceivable instrument. They will fade. They will disappear. And the observable universe, paradoxically, will shrink. Yes, the same universe that is expanding is also, from our point of view, getting smaller. The total volume of space is increasing. The volume we can see is decreasing. We live in a privileged moment, a moment when the universe is large enough to be filled with structure and still close enough that we can see most of it. A moment when distant galaxies are still detectable, when the afterglow of the Big Bang is still visible as faint microwave radiation, when the story of cosmic history can still be reconstructed by clever instruments and patient minds. In the deep future, none of this will be possible. A civilization rising on a planet around a red dwarf star 1 trillion years from now will look up at the sky and see only its own galaxy, alone in an infinite void. The cosmic microwave background will have redshifted into undetectability. Every other galaxy will have crossed the horizon. The universe will appear small, isolated, and silent. That civilization will develop physics. It will develop chemistry. It will likely never develop cosmology, because the evidence will have been hidden by the expansion of space itself. We exist in a window, a narrow window in cosmic time, when the universe still tells us its story. And in that window, we have measured the observable universe. We have counted its galaxies. We have traced its structures. And we have realized that the part we can see is almost certainly a fragment, possibly an inconceivably tiny fragment, of something that has no edge we can ever reach. Now, with that scaffolding in place, let us climb back into the structure of what we can see. Let us walk the ladder of cosmic scale from our local group of galaxies outward. The Milky Way is not alone. Andromeda, our nearest large neighbor, is on a collision course with us. In approximately 4.5 billion years, the two galaxies will merge in a slow gravitational dance, eventually forming a single large elliptical galaxy that astronomers have already nicknamed Milkomeda. Around the Milky Way and Andromeda, a swarm of smaller galaxies orbit. The Triangulum Galaxy, the large and small Magellanic Clouds visible from the southern hemisphere, the Sagittarius Dwarf, the Canis Major Dwarf, dozens of even smaller dwarf galaxies, some so faint they have only been discovered in the last decade. Together, these galaxies form what astronomers call the local group. The local group spans approximately 10 million light-years and contains roughly 100 galaxies. It is held together by gravity. It is one bound unit, drifting through space as a single object on the largest scales. And the local group is one of countless such groups in our cosmic neighborhood. Beyond the local group, the structure becomes denser. Tens of millions of light-years away lies the Virgo cluster, a massive concentration of more than 1/300 galaxies dominated by the giant elliptical galaxy M87, which contains the supermassive black hole that became the first black hole ever directly imaged in 2019. The Virgo cluster is one of many clusters in our region. Together, the Virgo cluster, the local group, and many other galaxy groups make up the Virgo supercluster, a structure roughly 110 million light-years across. For decades, astronomers thought the Virgo supercluster was the limit of organized structure in our region. It seemed to be the largest gravitationally relevant entity that contained us. Then, in 2014, a team led by R. Brent Tully of the University of Hawaii redrew the map. Using galaxy flow data, the velocities at which galaxies are moving through space relative to the cosmic expansion, they mapped not the visible structure, but the gravitational structure. They asked a different question: They asked which galaxies are flowing toward a common center, which galaxies share a single gravitational basin. The answer was breathtaking. The Virgo supercluster was not a supercluster at all. It was one lobe of something much larger. They called the larger structure Laniakea, a Hawaiian word meaning immense heaven. Laniakea contains the Virgo supercluster, the local group, the Milky Way, our sun, our planet, you. It spans 520 million light-years and contains approximately 100,000 galaxies. And all of those galaxies, including ours, are flowing toward a region near the center known as the Great Attractor. We are inside Laniakea. We are part of its slow gravitational pulse. We are falling, all of us, every star and every galaxy in our entire neighborhood, toward the Great Attractor at speeds of hundreds of kilometers per second. We will never get there. The accelerating expansion of space will pull us apart from it long before we arrive. But for now, in this brief cosmic moment, we are falling. And Laniakea itself is not the largest known structure. It is one lobe of an even larger filament, the Pisces-Cetus supercluster complex, which stretches approximately 1 billion light-years across the sky. 1 billion light-years of galaxies strung along a single thread of the cosmic web. And the cosmic web, that vast network of filaments and nodes and voids, fills the entire observable universe, the entire 93 billion light-year sphere. And the Pisces-Cetus complex, that 1 billion light-year structure, is roughly 1% of the diameter of the observable universe. The largest known structure is 1% of the visible region, which is itself an unmeasurably small fragment of the true universe. You are inside a galaxy, inside a local group, inside a supercluster complex, inside an observable universe, inside a true universe, whose boundaries, if they exist at all, are beyond any conceivable observation. Every layer of that address dwarfs the layer beneath it. Every step outward makes the steps before it feel like dust. And we have not yet talked about what fills the spaces between the structures. We have not yet talked about the voids. Because the structures we have been describing, the filaments, the clusters, the supercluster complexes, are not the dominant feature of the universe by volume. They are the minority. They are the bright threads in a much darker tapestry. The dominant feature of the universe at the largest scales is emptiness, not the empty space between stars in a galaxy, not the empty space between galaxies in a cluster, something on a scale that dwarfs even those, voids. In 1981, a team of astronomers led by Robert Kirshner at the University of Michigan was conducting a redshift survey. They were measuring the three-dimensional positions of galaxies, calculating not just where each galaxy appeared in the sky, but how far away it was. Routine work, necessary work, cataloging the cosmos one position at a time. And then, in a region near the constellation Bootes, they found a hole, a spherical region of space containing almost no galaxies. They checked the data. They rechecked the instruments. The hole was real. They had discovered the Bootes void. The Bootes void is approximately 330 million light-years across. To make that number mean something, consider that the entire Milky Way is 100,000 light-years across. You could line up more than 3,000 Milky Way galaxies end to end to span the width of the Bootes void. In a region of space that size, astronomers would expect to find roughly 2,000 galaxies. The Bootes void contains about 60 galaxies, scattered along a thin tube-like region running through the middle of the void. The rest is darkness. Almost nothing for hundreds of millions of light-years in every direction. The astronomer Greg Aldering once made a thought experiment that captures what this means. He said that if the Milky Way had happened to form near the center of the Bootes void, we would not have discovered other galaxies existed until the 1960s. We would have looked up at the night sky with the best telescopes of the early 20th century and seen nothing. No Andromeda, no Magellanic Clouds, no spiral nebulae to argue about. We would have lived our entire scientific history believing we were alone, the only galaxy in an infinite black sea. And we would have been wrong, but we would have had no way to know it. Our cosmology would have been a beautiful, careful, completely incorrect picture of a universe vastly smaller than the real thing. The Bootes void is not an outlier. It is not a strange anomaly. It is one example of a feature that dominates the cosmos. Voids make up approximately 80% of the volume of the observable universe. 80%. The vast majority of space is not filled with galaxies or stars or planets or anything we would recognize as matter. It is filled with almost nothing. The galaxies cluster along the thin walls and filaments between the voids, like soap film clinging to the surfaces of enormous bubbles. The universe at its largest scale looks like foam, like a froth of empty cells, separated by impossibly thin membranes where matter has gathered. The bubbles are the voids. The membranes are everything we have ever seen. And here is something that should change how you think about your address. You live inside a void. The Milky Way sits within what astronomers call the KBC void, also known as the local hole. It was identified and studied in 2013 by Ryan Keenan, Amy Barger, and Lennox Cowie. The KBC void is a region of below-average galaxy density, roughly 2 billion light-years across. 2 billion. That is more than 6 times the diameter of the Boots void. We are not in a typical part of the universe. We are not in a dense filament or a bustling galaxy cluster. We are in the cosmic countryside, a region where the density of galaxies is 15 to 50% lower than the cosmic average. The Milky Way sits within a few hundred million light-years of the center of this underdensity. We are inhabitants of a hollow, residents of a thin spot in the cosmic foam, and this address might matter more than it sounds. Some researchers have proposed that our location inside the KBC void could be partly responsible for the Hubble tension, the increasingly serious discrepancy between two ways of measuring how fast the universe is expanding. The reasoning is straightforward. Galaxies inside a void experience a gentle gravitational pull from the denser regions outside the void. That pull subtly accelerates the local rate of expansion, making the universe appear to be expanding faster in our neighborhood than the cosmic average would suggest. If the KBC void is real, and if we are near enough to its center, then the local measurements of the expansion rate would naturally come out higher than the value derived from the early universe. The discrepancy would not be a sign of broken physics. It would be a sign that our particular vantage point in the cosmos is unusual. Data analyzed in 2025 using baryon acoustic oscillation measurements suggested that a void model is approximately 100 million times more likely than a void-free model consistent with the cosmic microwave background. The debate continues. The implication does not. Our view of the universe, our measurement of its most basic property, the rate at which it is growing, may be distorted by where we happen to be standing. The map is not the territory. The view is not the universe. We are observers inside a structure, and the structure shapes what we see. So how did the voids form? Why is 80% of the cosmos a desert? The answer reaches all the way back to the first fraction of a second after the Big Bang. When the universe was born, it was hot, dense, and almost perfectly uniform. Almost, because perfect uniformity is impossible in a universe governed by quantum mechanics. At quantum scales, fields fluctuate. Density wavers. Energy ripples in and out of existence in random patterns smaller than atoms. In the calm ocean of the early universe, these fluctuations were ripples 1 part in 100,000, smaller than a millimeter on a surface stretching thousands of kilometers. Unimaginably faint, statistically invisible to any instrument from any era. And then, inflation happened. In the first 10 to the minus 32nd of a second, the universe expanded exponentially. Space stretched by a factor of at least 10 to the 26th. A region smaller than a proton ballooned into something larger than the observable universe today, and those tiny quantum fluctuations, those subatomic ripples, got stretched along with everything else. They were inflated to cosmic scales. They became density variations spanning thousands of light years. After inflation ended and the universe began its normal expansion, those variations were there, frozen into the fabric of space. Tiny differences in density, almost imperceptible. 1 part in 100,000. But gravity is patient. Gravity is relentless. Over billions of years, gravity amplified those differences. Regions that started slightly denser than average pulled a little more matter toward themselves. Their gravity grew slightly stronger, which pulled in more matter, which grew their gravity further. A feedback loop. Regions that started slightly less dense lost matter to their richer neighbors. Their gravity grew weaker. They emptied out. Slowly, over the entire history of the cosmos, the differences amplified. The dense regions became filaments and clusters. The empty regions became voids. The cosmic web took shape, not because the universe was designed that way, but because gravity ran wild over 13 billion years on the seeds planted by quantum mechanics in the first instant. Everything you see, every galaxy, every star, every atom in your body, is the amplified echo of a quantum jitter that occurred before the universe was a second old. We owe our existence to noise in a field that did not yet have a name. If those initial fluctuations had been smoother, no structure would have formed. The universe would be a thin, expanding gas of hydrogen and helium, gradually cooling forever. No galaxies, no stars, no anyone to notice. If those fluctuations had been larger, gravity would have run away too quickly. Dense regions would have collapsed directly into black holes before stars could form. The universe would be a graveyard of black holes drifting through empty space. The fact that the fluctuations were exactly the right size, 1 part in 100,000, neither too smooth nor too rough, is one of the most remarkable features of the cosmos. Change that number even slightly and we are not here. The universe is empty in the way it is for a reason. And that reason traces back to the quantum field equations that govern the universe in its first impossible instant. So we have walked from the surface of Earth to the cosmic web. We have crossed the solar system, the galaxy, the local group, the supercluster complex. We have stood inside a void. We have looked out at the foam of structure that fills the observable universe. And now we have to talk about what is actually there. Because the matter you can see, the galaxies and stars and planets and gas clouds, the things we have been mapping for the last hour of this journey, do not add up. They never have. In the 1930s, the Swiss astronomer Fritz Zwicky was studying the Coma cluster, a massive collection of galaxies roughly 320 million light-years from Earth. He measured how fast the galaxies in the cluster were moving relative to each other. From those motions, he could calculate how much total mass the cluster must contain to hold itself together gravitationally. Then, he counted the visible matter, the stars, the gas, the dust. He calculated the mass of everything he could see, and the numbers did not match. Not even close. The cluster contained far more mass than its visible contents could account for. The galaxies were moving so fast that, based on the visible mass alone, they should have flown apart millions of years ago. Something invisible was holding the cluster together. Some unseen mass was providing the extra gravitational glue. Zwicky calculated that the cluster needed at least 400 times more mass than he could see. He called the missing material Dunkel Materie, dark matter. For decades, the idea was largely ignored. It sounded absurd. Invisible matter that had mass but did not emit light or absorb light or interact with any electromagnetic radiation at all. It violated common sense. Surely Zwicky had made a mistake. Surely there was some other explanation. Then in the 1970s, the American astronomer Vera Rubin made the same discovery on a different scale. She was measuring the rotation speeds of stars within individual spiral galaxies. According to Newtonian gravity, stars near the edge of a galaxy should orbit more slowly than stars near the center. The farther you are from the galactic core, the weaker the gravitational pull, the slower the orbit. Just as Pluto orbits the Sun more slowly than Mercury, Rubin found something different. The stars at the edges of galaxies were not orbiting more slowly. They were orbiting just as fast as stars closer in, sometimes faster. The rotation curves were flat. It made no sense. Unless there was extra mass extending far beyond the visible disk of each galaxy. An invisible halo of matter providing the additional gravitational pull needed to keep those outer stars moving so quickly. Rubin had independently confirmed Zwicky. Galaxies were embedded in halos of dark matter, vast spherical clouds of invisible mass that dominated their gravity. Since then, the evidence has piled up from every direction. Galaxy clusters bend the light of background objects by amounts that visible matter cannot explain. The cosmic microwave background contains patterns that only make sense if dark matter was present in the early universe, creating gravitational wells into which ordinary matter fell. The cosmic web itself would not form without dark matter. Simulations that include only ordinary matter produce a universe that looks nothing like what we observe. Add dark matter, and the web emerges. The filaments form. The voids open. The galaxies cluster at the nodes. Every independent line of evidence points to the same conclusion. Most of the matter in the universe is invisible. It does not emit light. It does not absorb light. It does not reflect light. It interacts with ordinary matter only through gravity. And it outweighs ordinary matter by a factor of approximately 6 to 1. For every kilogram of normal matter in the universe, there are 6 kilograms of dark matter. The galaxies we see, the stars, the planets, the gas, the dust, the atoms that make up your body, all of it together makes up about 5% of the total mass energy content of the universe. Dark matter makes up about 27%, 5 times more dark matter than visible matter. And we still do not know what it is. Dozens of experiments around the world are hunting for dark matter particles. Underground detectors shielded from cosmic rays by kilometers of rock, designed to catch the faint signal of a dark matter particle bouncing off a normal atom. Particle accelerators smashing protons together at energies high enough to create dark matter in the debris. Space telescopes searching for the gamma-ray signatures of dark matter particles annihilating each other in the cores of galaxies. After decades of searching, we have nothing. No confirmed direct detection. We know dark matter is there. We can map its distribution from its gravitational effects. We can predict its behavior with remarkable accuracy. We cannot find the particle. It is the most abundant kind of matter in the universe, and we do not know what it is. And dark matter is not even the strangest part of the inventory. 27% of the universe is dark matter. 5% is visible matter. That accounts for 32%. The remaining 68% is something else entirely. In 1998, 2 independent teams of astronomers were measuring the expansion history of the universe using a particular type of exploding star called a Type Ia supernova. Type Ia supernovae are useful because they all reach roughly the same peak brightness. They are standard candles, objects whose intrinsic luminosity is known. Measure how bright a Type Ia supernova appears from Earth, compare it to how bright it actually is, and you can calculate its distance with high precision. Both teams were trying to determine how much the expansion of the universe was slowing down, because that was the expectation. After the Big Bang, all the matter in the universe started flying apart. Gravity should be working against that expansion, gradually pulling everything back together, slowing the expansion over time. The question was simply how much. Was there enough matter to eventually halt the expansion and cause the universe to recollapse in a big crunch? Or would the expansion continue forever but at a steadily decreasing rate? Neither. The data showed that the expansion of the universe was not slowing down. It was speeding up. Distant supernovae were dimmer than expected, which meant they were farther away than expected, which meant the universe had expanded more than expected since the light left those stars. Something was pushing space apart. Something was overcoming the gravitational pull of all the matter in the universe and accelerating the expansion. Both teams independently arrived at the same impossible result. The expansion of the cosmos is accelerating, and something we cannot see is driving it. They called the something dark energy. The name is a confession. It is dark because we cannot see it. It is energy because it does work, accelerating the expansion of space. Beyond those 2 words, we know almost nothing about it. Current measurements suggest that dark energy makes up roughly 68% of the total mass energy content of the universe. Combine that with 27% dark matter, and you get 95% of the universe that is something we do not understand. 5% is ordinary matter. 5% is everything you have ever seen. 5% is the entire visible universe. Stars, galaxies, gas, dust, planets. Every atom that makes up your body and your house and your planet and your star. 5%. 95% is invisible. 27% of that 95 we can at least map gravitationally. 68% of it we can barely describe except by its effect on the expansion of space. We live in a universe overwhelmingly composed of things we do not understand. The visible cosmos is a thin, luminous skin stretched over an abyss of unknown forces. The cosmic web, the largest structure in existence, is built on a scaffold of dark matter we have never directly detected, and it is being torn apart by a dark energy we cannot explain. We have telescopes powerful enough to photograph a single strand of the cosmic web stretching 3 million light-years between two ancient galaxies, which we did for the first time in 2025. We have instruments precise enough to detect the gravitational waves from black holes colliding a billion light-years away. We have computers capable of simulating the entire history of the universe from the first fraction of a second after the Big Bang to the present day. And we still do not know what most of the universe is made of. So when we ask how big the universe really is, we have to admit that the question contains hidden assumptions we cannot defend. The size of the observable universe depends on the rate of expansion. The rate of expansion depends on dark energy. Dark energy is something we do not understand. The size of the true universe beyond the observable region depends on the model of inflation, which depends on physics that operates at energies we cannot reproduce in any laboratory. Our best estimates are educated guesses built on theories that may or may not be correct. The truth is that the universe is not just larger than we can see. It is larger than we can model. The numbers we work with, the 93 billion light-years across, the 2 trillion galaxies, the 10 to the 24th stars, all describe the visible region. Beyond that region, the numbers become uncertain. They depend on assumptions. They reach values that the human brain cannot meaningfully compare to anything. Let us try a thought experiment. Take the observable universe. The full 93 billion light-year sphere containing 2 trillion galaxies. Shrink it down in your mind until it fits inside a single coin held in your hand. A €1 coin, a quarter, whatever object is comfortable to imagine. Now, according to conservative estimates based on the flatness of space measured from the cosmic microwave background, the full universe is at least 250 times larger than the observable region. So in our shrunken model, if the observable universe is a coin, the full universe is a sphere at least about the size of a small swimming pool. Already that is unsettling. Everything you have ever seen, every galaxy, every star, every photon that has ever reached human eyes from any direction, fits inside the coin. The rest of the universe, the part we will never see, fills the swimming pool. And the swimming pool is the conservative estimate. The floor, the smallest the universe can be while remaining consistent with our measurements. Now consider the inflationary estimates. Some inflationary models put the true universe at 10 to the 23rd times larger than the observable region. In our coin analogy, if the observable universe is the size of a €1 coin, the full universe is a sphere roughly 250,000 light-years across, larger than the diameter of the Milky Way galaxy. The observable universe, the entire region we can see, is a coin, and the full universe, in that scenario, is bigger than our entire galaxy. And some models go further. Some inflationary scenarios predict that the universe is literally infinite, not just large, not just unimaginably large, infinite, extending without boundary in every direction. If the universe is infinite, then every possible arrangement of atoms occurs somewhere. With finite possible configurations of matter and infinite space to arrange them in, repetition is not just possible, it is guaranteed. Somewhere, light-years beyond any horizon we will ever cross, there is a copy of Earth, a copy of you, a copy of this exact moment, not as metaphor, as mathematical certainty, hidden in the structure of an infinite cosmos. There are other versions of every choice you have ever made and every choice you did not make, every life that could have been lived, every history that could have unfolded, all of them real, all of them somewhere, all of them forever beyond the reach of your observation. This is the conclusion that follows logically from the data and the leading theory of cosmic origins. It cannot be confirmed, it cannot be tested. It may not even be true, but it is consistent with the evidence, and it is one of several possibilities that physicists take seriously when they try to estimate the true size of the cosmos. Now, you might object. You might say, all right, the universe is bigger than the observable region, but we will never see it. Why does it matter? It matters because it changes the meaning of every measurement we make. Every number we have ever calculated about the size of the universe, the number of galaxies, the density of matter, the rate of expansion, applies only to the observable region. We are measuring our keyhole. We have no idea whether our keyhole is representative of the room beyond it. Imagine a fish that has lived its entire life inside a small bay. The bay is rich with coral and other fish and currents. The fish has mapped the bay carefully. It has counted the species. It has measured the depth. It has even understood the cycles of the tides. And the fish believes, reasonably, that it has understood the ocean. Then one day, far in the future, the fish's descendants discover that the bay is connected to a much larger ocean, an ocean of which the bay is a microscopic feature, an ocean containing realms the bay's inhabitants never imagined. And the descendants realize that everything their ancestors knew about the ocean was technically true within the bay, but mostly irrelevant on the larger scale. We are the fish. The observable universe is our bay. And the ocean of the true universe stretches in every direction beyond any horizon we will ever cross. We have measured our bay very carefully. We have counted its galaxies and traced its filaments. We have calculated its expansion rate to high precision. We have done excellent work on our small region, and we have to be honest about what that work means. It means we understand our patch. It does not mean we understand the universe. So how big is the universe really? The honest answer is that we do not know. We know the observable universe is approximately 93 billion light-years across. We know the total universe is at least 250 times larger by volume. We know the total universe might be 10 to the 23rd times larger. We know it might be infinite. We know that whatever the true size is, we will never measure it directly. Most of it will always be beyond our reach. And we know that the part we can see is one fragment of one bubble in what may be a multiverse. The multiverse, we have to talk about it. Because if cosmic inflation happened, and the evidence strongly suggests it did, then most models of inflation predict that inflation does not stop everywhere at once. Inflation is not a single event. It is a process driven by a quantum field that filled all of space. In our region, that field decayed. Inflation ended. Matter formed. Galaxies emerged. Stars ignited. But in other regions so far beyond our horizon that the word distance loses its meaning, the field may not have decayed. Inflation may still be happening. Right now, somewhere unimaginably far beyond the edge of what light can ever reach, space is inflating exponentially, producing more space, in which pockets of decay are forming, in which new big bangs are happening, in which new universes are emerging. Some of those universes may have physics very similar to ours. Stars and galaxies and chemistry, and perhaps even life. Some may have physics so different that nothing recognizable could exist. Universes where the strong nuclear force is too weak for atoms to hold together. Universes where the cosmological constant is large enough to tear space apart before any structure can form. Universes with fewer or more spatial dimensions. Universes whose constants of nature are tuned to values that produce nothing but radiation, expanding forever into formless heat. The multiverse is not a science fiction concept. It is a logical consequence of the same physics that produced our universe. If inflation is real, and it appears to be, then the framework that produced our cosmos almost certainly produced others. Not somewhere we can visit, not somewhere we can detect, just somewhere. Bubbles in an inflating ocean, each one isolated from every other by an infinite gulf of accelerating expansion. We sit inside one bubble, looking out at a sliver of it, asking how big our bubble is, and unable to see the ocean it floats in. Some critics dismiss the multiverse as untestable, as metaphysics dressed up in equations. They have a point. We cannot confirm the existence of other universes by direct observation. We may never be able to. But the multiverse is not an arbitrary hypothesis. It is a prediction of the inflationary models that have passed every observational test so far. If we accept the part of inflation that explains the uniformity and flatness of the observable universe, we cannot easily reject the part that predicts other bubbles. The mathematics does not let us cherry-pick. And there are faint hints, far from conclusive, that the multiverse might leave fingerprints. If two bubble universes formed close enough together in the inflating substrate, they might have collided. A bubble collision would leave a specific pattern in the cosmic microwave background, a circular bruise of slightly different temperature in the ancient light. Some researchers have claimed to identify such features in the data. Cold spots, asymmetries, patterns that do not fit the simplest models. The statistical significance is below the threshold for discovery. But the features are there, sitting at the edge of the data like shadows at the periphery of vision. Possible echoes of other universes brushing against our own 13 billion years ago. Or possibly just statistical noise. We do not yet know. So when we ask how big the universe is, the answer depends on what we mean. If we mean the part we can see, the answer is 93 billion light-years across. If we mean the part that exists, including regions whose light will never reach us, the answer is at least 250 times larger, possibly 10 to the 23rd times larger, possibly infinite. If we mean all of reality, including other bubble universes in an inflating multiverse, the answer is that the word size may not even apply. The multiverse does not have a boundary in any meaningful sense. It does not have a center. It does not have an edge. It is a structure of nested infinities, expanding forever, producing endless variations on the theme of existence. Our universe is one note in that symphony, one bubble in that ocean, one frame in a film that has no beginning and no end and no audience who can ever see the whole thing. And we sit on a small planet orbiting an average star in a minor arm of one galaxy of 2 trillion, in the visible region of one bubble of an infinity of bubbles, asking the question. And the question itself, the act of asking, may be the most extraordinary feature of the entire cosmos. Because in all that vastness, in all those galaxies, in all those stars, in all those bubbles, the universe has organized matter into a configuration that can ask how big it is. That is not nothing. That may be the only thing that matters. The matter in your body was forged in the cores of stars and scattered by supernovae across hundreds of millions of years. It drifted through interstellar gas. It collected in the cloud that formed our solar system. It coalesced into rock and water and eventually into a thin film of life clinging to the surface of one rocky world. Over 4 billion years, that life evolved. Over a few 100,000 years, one species emerged that could look up. Over the last few centuries, that species built instruments capable of measuring the size of the cosmos. And here you are, the end of a 4 billion year chain of evolution, and a 13.8 billion year chain of cosmic history asking the question. We do not yet have a complete answer. We may never have one. But we have managed, on this small wet rock, to calculate that the visible universe is 93 billion light-years across, contains 2 trillion galaxies, is built on a scaffold of dark matter we cannot directly detect, is being torn apart by a dark energy we cannot explain, and is almost certainly a fragment of something far larger. That calculation, performed by beings whose entire civilization is younger than the light still arriving from the nearest galaxy, is one of the most extraordinary feats in the history of life. We have measured the keyhole. We have understood that it is a keyhole. We have estimated, however imperfectly, the size of the room beyond it. And we have done all of this in a moment of cosmic history so brief that, on the scale of the universe's lifespan, it has barely happened. We are still here. The galaxies are still close enough to see. The cosmic microwave background is still detectable. The story of the cosmos is still readable in the patterns of the sky. In a trillion years, none of this will be possible. Most of the galaxies will have crossed the cosmic event horizon and disappeared. The microwave background will have redshifted into undetectability. Future civilizations, if any arise, will look up and see only their own galaxy floating in apparent isolation. They will develop physics. They will study their local star. They may never know that the universe began in a hot, dense state 13 billion years before their measurements started. They may never know that the universe expanded. They may never know that other galaxies existed. The evidence will be gone, erased by the same expansion that produced them. We exist in a window. A narrow window in cosmic time when the universe is still telling its story. And in that window, we have made the universe answer some of its oldest questions. We have measured the speed of light. We have measured the expansion of space. We have detected the afterglow of the Big Bang. We have photographed the cosmic web. We have inferred the existence of dark matter and dark energy. We have estimated the size of the observable universe to within a few percent. We have done all of this, and we have done it well. And the universe, in answering, has revealed that it is larger than any answer we are equipped to give, larger than our instruments can reach, larger than our brains can picture, larger than our species will ever survive to fully explore. The answer to the question, how big is the universe really, is that the universe is big enough to break the question. It is big enough that the framework we used to ask it cannot hold the answer. It is big enough that we have to invent new vocabulary, new mathematics, new frameworks of thought, just to discuss the parts of it we will never see. And we are still trying. Because every time the universe breaks one of our questions, we build a new one. We extend the framework, we push deeper, we keep going. That is what makes the journey worth taking, even though the destination is unreachable. And the journey is not over. We have walked from the Earth to the multiverse. We have crossed 13 billion years of cosmic history. We have stood inside voids, the size of continents, the size of countries, the size of nothing we have words for. But there is more to see. There are corners of the cosmos we have not yet touched. There are mysteries that go deeper than the size of space. There is a galaxy that should not exist, photographed by a telescope a million miles from Earth, that has rewritten what we thought we knew about the early universe. There is a tension at the heart of cosmology that may be telling us our model of reality is broken. There is a question about what happens at the edge of sight, where light fades, where the cosmic event horizon falls, where some galaxies are already lost to us forever. And beyond all of that, there is the deepest question of all, the question we have not yet asked. The question that the size of the universe makes impossible to escape. Are we alone? Not in the sense that there is no one else. The numbers suggest that life of some kind is probably common. With 10 to the 24th stars in the observable universe and a reasonable fraction of them hosting habitable planets, the odds of life arising elsewhere seem strong. The question is not whether anyone else is out there. The question is whether we will ever know. Because the universe is not just big, it is structured to keep its inhabitants apart. The voids separate galaxies by hundreds of millions of light years. The expansion of space carries galaxies away from each other faster than any signal can cross between them. The cosmic event horizon seals off the majority of the cosmos permanently. Even within our own galaxy, communication across the full 100,000 light-year diameter would take 100,000 years for a single message to arrive. Civilizations could rise and fall in the time it takes one to say hello to another. And we have been broadcasting for only about a century. Our radio signals, the fastest signals we can produce, traveling at the speed of light, have reached a sphere about 125 light-years in radius around Earth, a sphere that contains a few thousand stars. In a galaxy of 400 billion, we are a whisper inside a cathedral. We have not been heard by anyone. We may never be, not because no one is out there, but because the cosmos is too large, and the time too short, and the distances too brutal for anyone to ever bridge. The universe may be teeming with voices, all of them calling out, all of them unheard, all of them isolated by the same architecture that produced them. And that architecture, the foam of voids, the threads of filaments, the expanding ocean of space, may be the answer to the oldest question. Not why is no one talking to us, but why the universe is built in a way that makes talking nearly impossible. We are going to come back to that question. We are going to look at what James Webb has shown us about galaxies that should not exist. We are going to confront the Hubble tension and what it might mean for the model of the cosmos we have spent a century building. And we are going to follow the evidence as far as it will take us. But first, we need to look at one more layer of the picture. Because everything we have discussed so far, every void and filament, every dark matter halo, every quantum fluctuation amplified across 13 billion years, every estimate of the size of the cosmos, rests on a single assumption that we have not yet examined. The assumption that the laws of physics are the same everywhere. This assumption has a name. Cosmologists call it the cosmological principle. It states that on large enough scales, the universe looks the same in every direction and from every location. No special places, no preferred axis, no region where the rules are different. Pick any large enough patch of the cosmos, average over its contents, and you should get the same density, the same composition, the same physics as any other patch of the same size. This principle is not a piece of philosophy, it is mathematics. Without it, the equations that describe the universe's evolution become essentially unsolvable. Every model we have ever built of the cosmos depends on it. Every prediction we have ever made about the early universe relies on it. Every estimate of the size of the cosmos assumes it. And we cannot test it across the regions we cannot see. We can only test it inside our observable bubble, and even there, only on the largest scales. On smaller scales, the universe is obviously not uniform. There are stars, and there is empty space. There are galaxies, and there are voids. Local lumpiness is the rule, not the exception. The cosmological principle only requires uniformity, averaged over very large distances. And on those distances, it appears to hold. Surveys of galaxy distributions over hundreds of millions of light-years suggest that the universe does become statistically uniform when averaged over large enough patches. The cosmic microwave background, the most ancient light we can detect, is uniform to within 1 part in 100,000 across the entire sky. Whatever happened in the early universe, it happened the same way everywhere we can see. So far, so good. The principle is consistent with the data. But here is the uncomfortable part. We have been finding structures that may violate it. In 2013, astronomers reported the discovery of a structure called the Hercules Corona Borealis Great Wall. It is a concentration of galaxies stretching approximately 10 billion light-years across the sky. 10 billion. To put that in perspective, the observable universe is about 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall is roughly 1/9 of the entire observable universe. Theoretical models of structure formation place a ceiling on how large any single structure can be at this point in cosmic history. The ceiling is roughly 1.2 billion light-years. The Hercules Corona Borealis Great Wall is nearly 10 times that limit. If the structure is real, it represents a violation of the cosmological principle, a genuine large-scale departure from uniformity. The existence of the Great Wall has been debated since its discovery. Some researchers argue that the apparent structure is a statistical artifact, that gamma-ray bursts, which were used to identify it, are biased tracers of galaxy distribution. Others have published follow-up studies arguing that the structure is real and that conventional cosmology cannot easily explain it. The debate continues. The implication remains unresolved. And the Hercules Corona Borealis Great Wall is not alone. In 2024, a separate team announced the detection of a structure called the Big Ring, a nearly circular alignment of galaxies and galaxy clusters approximately 1.3 billion light-years in diameter. The same year, another team described the Giant Arc, a curving structure of galaxies roughly 3.3 billion light-years long. Neither of these features fits comfortably inside the cosmological principle's expected limits. Both are real. Both are documented in peer-reviewed literature. Neither has yet been satisfactorily explained. So we are in a strange position. The cosmological principle is the foundation of modern cosmology. It is built into every equation we use to estimate the size, age, and content of the universe. And it may be wrong, or at least incomplete, or at least challenged by structures we cannot ignore. If the principle fails, the consequences are profound. The age of the universe, calculated from the cosmic microwave background under the assumption of uniformity, would need to be reassessed. The expansion rate, measured against the assumption that we live in a typical region, would need to be recalibrated. The estimates of the size of the universe beyond the observable region, which rely entirely on the assumption that the parts we can see are representative of the parts we cannot, would lose much of their meaning. We would be back at the beginning, trying to map an ocean from inside a bay, no longer confident that the bay is typical of the sea around it. This is the position we are actually in. We do not know it yet. The mainstream of cosmology continues to use the cosmological principle as a working assumption because the alternatives are too messy to compute with. But the cracks are showing. The model is straining, And the data, especially the data coming back from new telescopes, keeps making the cracks wider. Now we come to the telescope that has done more to widen the cracks than any instrument in the last quarter century. The telescope that was supposed to confirm our picture of the early universe and instead has been quietly dismantling it. The telescope sitting 1,000,000 miles from Earth, staring backward through time. The James Webb Space Telescope. James Webb was launched on December 25, 2021. It took 25 years to design and build. It cost $10 billion. It carries a primary mirror 6.5 meters across, plated in gold, designed to capture infrared light from the deepest reaches of the cosmos. It sits at the second Lagrange point, a gravitationally stable position roughly 1.5 million kilometers from Earth, where it orbits the Sun in synchronized step with our planet, shielded from the Sun's heat by a 5-layer sun shield the size of a tennis court. Its instruments are cooled to within a few degrees of absolute zero. Its detectors are sensitive enough to register the faint red-shifted light from galaxies whose photons have been traveling toward Earth for more than 13 billion years. It was built to look at the early universe, to see the first galaxies, to confirm what our models predicted should be there. And almost from the moment it began returning data, it started showing us things that should not exist. In January of 2026, NASA confirmed the most distant galaxy ever detected. It is called MOM-ZES 14. The name comes from the survey program that identified it. The Z14 refers to its redshift, a measure of how much its light has been stretched by the expansion of space. A redshift of 14.4 means the light from MOM-Z14 has been traveling through expanding space for more than 13.5 billion years. We are seeing this galaxy as it appeared just 280 million years after the Big Bang. The universe was 2% of its current age. And according to every model we had before James Webb launched, a galaxy that early should be small, dim, simple. A faint cloud of primordial gas just beginning to gather itself into the first wisps of structure. There had not been enough time for stars to live and die and produce heavy elements. There had not been enough time for galaxies to grow large or bright or organized. MOM-14 defies all of it. It is intensely luminous. Its absolute ultraviolet magnitude is -20.2, brighter than essentially anything models predicted for its epoch. It is compact, with an effective radius of only about 74 parsecs, roughly 240 light-years across. And it shows elevated levels of nitrogen, an element that normally requires multiple generations of stars to produce. In a galaxy seen just 280 million years after the Big Bang, the presence of nitrogen suggests that something unusual is happening. Massive stars are forming, dying, and enriching their surroundings far faster than standard stellar evolution allows. The galaxy has also begun to clear the surrounding hydrogen fog. The early universe was filled with neutral hydrogen, a thick gas that absorbed ultraviolet light and made the cosmos opaque to certain wavelengths. The epoch of reionization, when the first stars and galaxies produced enough ultraviolet radiation to ionize that gas and make the universe transparent again, was supposed to be a long, slow process that did not really get started until much later. MOM-ZES-14 is already doing it, just 280 million years after the Big Bang. The lead researchers, including Rohan Naidu of the Massachusetts Institute of Technology, did not hide their reaction. They said it plainly. With Webb, we can see farther than humans ever have before, and it looks nothing like what we predicted. Nothing like what we predicted. That is not a small statement. That is a confession that the framework we built over the last 25 years to explain how galaxies form, when they form, and what they should look like at any given moment in cosmic history, is producing answers that the universe refuses to honor. And MOM-Z14 is not alone. James Webb has now identified more than 100 bright galaxies at redshifts above 10. In an era where the consensus models predicted essentially none, the number density of bright galaxies at this distance is more than 100 times larger than what the standard model expected. Not slightly larger. Not double. 100 times larger. Among the most striking discoveries is a galaxy called Zhulong, identified in observations published in 2025. Zhulong sits at a redshift of about 5.22. It is older than MOM-Z14, but still extraordinarily young by cosmic standards. We are seeing it as it appeared roughly 1 billion years after the Big Bang. And what we see is not a young galaxy. Zhulong is an ultra-massive grand design spiral. It has spiral arms. It has a mature central bulge. It contains roughly 100 billion solar masses worth of stars. It looks like a galaxy that has had billions of years to evolve. It had 1 billion. Galaxies like Zhulong are not supposed to exist that early. Spiral structure requires that the galactic disk has had time to settle into a coherent rotating system. Central bulges require repeated mergers and infall of gas over extended periods. Assembling 100 billion solar masses of stars in 1 billion years pushes the limits of what any conventional model of star formation can produce. And yet, there it is. Fully formed, beautiful, impossible. Jacob Shen, a postdoctoral researcher at the Massachusetts Institute of Technology and a member of the MOAM-Z14 team, summarized the situation diplomatically. He said there is a growing chasm between theory and observation related to the early universe. Growing chasm, that is not the language of routine science. That is the language of a field facing an emergency. To be clear, the Big Bang itself is not in question. The evidence for it is overwhelming and comes from independent lines of inquiry. The cosmic microwave background, the observed expansion of space, the abundance of light elements produced in Big Bang nucleosynthesis, which precisely matches predictions across the universe. These pillars stand firm. The universe began in a hot, dense state, approximately 13.8 billion years ago. That part is settled. What is breaking is the timeline. The sequence of events that the standard model of cosmology predicts should follow the Big Bang. According to that model, structure should grow slowly. Small galaxies form first. They merge over hundreds of millions of years into larger galaxies. Bright, massive, structured galaxies should not appear until the universe is well into adolescence, several billion years old at minimum. James Webb is showing us something different. Galaxies are forming faster than the models allow. They are brighter than they should be. More massive. More chemically enriched. More structured. They look old when they should look young. Proposed solutions have started to pile up. Some researchers suggest that star formation in the early universe was far more efficient than the models assumed. Perhaps the dense conditions of the early cosmos allowed gas to collapse into stars at rates that vastly exceeded anything we see in the nearby universe. Others propose early dark energy, a hypothetical extra component that briefly accelerated the growth of structures in the first few 100 million years, and then faded away. Others suggest modifications to dark matter, perhaps allowing dark matter particles to interact with each other in ways that enhanced gravitational collapse in the early universe. Some have even invoked new particle physics, fields and forces beyond the standard model that operated in the first epochs of cosmic history. None of these solutions completely works. None resolves every anomaly without creating new ones. The field is in productive theoretical chaos, which is exactly the state that precedes major breakthroughs. And the chaos is not limited to the early universe. The Hubble tension is reaching a breaking point as well. Recall that the Hubble constant measures how fast the universe is expanding. Two methods of measuring it. One based on the cosmic microwave background and a model of cosmic evolution. The other based on direct distance measurements to relatively nearby objects. The two methods disagree. By 2025, the disagreement crossed the threshold that physicists use to declare a discovery. 5 sigma. The same threshold used to confirm the Higgs boson. The probability that the discrepancy is due to random chance is less than 1 in 3.5 million. Something is wrong. Daniel Skolnick of Duke University, one of the researchers at the front of this work, has put it as bluntly as anyone. He said the community needs to start acknowledging that this is more serious than a measurement discrepancy. It may be a sign that our model of cosmology is broken. In 2024 and 2025, the team behind the local measurement used James Webb to re-observe the same pulsating stars that had anchored their earlier estimates. The goal was to check whether dust or instrument error might be biasing the data. The result was clear. The earlier measurements were correct. The local expansion rate is genuinely faster than the rate predicted by the early universe data. In December of 2025, a separate team using gravitational lensing watching how light from distant quasars bends around foreground galaxies, published an independent measurement. They matched the local value. Every new technique that probes the local universe gets the same answer, and it is the wrong answer according to the standard model. The simplest possibility is that we are missing physics. That something happened in the early universe that subtly altered the patterns imprinted in the cosmic microwave background, shifting the value we derive from it. Early dark energy is one candidate. Primordial magnetic fields, faint magnetic structures that may have existed from the first moments of cosmic history are another. New neutrino species, additional types of subatomic ghost particles beyond the three we know about, are a third. Each of these proposals tries to bend the model just enough to reconcile the measurements. Each one creates new tensions in other parts of the data. None has been accepted as the answer. But the possibility remains that the question itself, how fast is the universe expanding, may be telling us that our picture of reality is incomplete in a fundamental way. And then there is the third anomaly. Dark energy itself may not be what we thought it was. For decades, the simplest model of dark energy has been the cosmological constant. A fixed energy density baked into the fabric of space itself, uniform across all of space, unchanging across all of time. It has one value, everywhere, always. This is the elegant version. The version that fits the math and is easy to work with. But the early results from a survey called the Dark Energy Spectroscopic Instrument, combined with measurements from James Webb and ground-based telescopes, are producing a hint. Only a hint, not yet a confirmation. The data appears to favor a scenario in which dark energy is not quite constant. Its strength may have varied subtly across cosmic time. If this turns out to be correct, it means the cosmological constant is not the right description of dark energy. Instead, dark energy would be a dynamic field, evolving over time, with its strength rising or falling across the eons. This would be a major shift in how we understand the universe. It would change the predictions for the long-term future of the cosmos. It might even change the predictions for the long-term past. A universe driven by a changing dark energy could expand differently in its earliest moments, could produce different patterns of structure, could explain some of the anomalies that have been piling up. We do not yet know if dark energy is changing. The hint is faint. The statistical significance is below the threshold for discovery. The next decade of measurements will tell. But the possibility is real. The possibility that the energy driving the largest scale behavior of the cosmos is not a constant at all. That the universe is not just expanding. It is expanding in ways that depend on a force we do not understand, varying in ways we did not predict, leading to outcomes we cannot yet calculate. Add up the picture. The standard model of cosmology, the framework that has dominated our understanding of the universe for 25 years, is facing three simultaneous crises. The early universe contains galaxies that should not exist. The expansion rate of the local universe disagrees with the rate predicted from the early universe at a statistical threshold normally reserved for declaring discoveries. And the dark energy that drives the universe's largest scale behavior may not be the constant we thought it was. Any one of these problems could in principle be solved by refining the existing model. But all three at once suggests something deeper. Suggests that our picture of the cosmos may need a structural revision, not a small correction. Not a tuning of parameters. A new framework. We're not there yet. The framework has not been found. But the field is increasingly willing to admit that the old framework cannot hold all of the evidence. And this matters for our question about size. Because the size of the universe, the rate of its expansion, the age of its galaxies, the structure of its largest features, all of these are calculated using the model that is now showing cracks. If the model needs revision, the numbers may shift. The observable universe might be slightly larger or slightly smaller than the current 93 billion light-year estimate. The age might be revised upward or downward. The total universe, the part beyond the observable region, might turn out to be vastly larger or vastly different from the current best guesses. We are not at the end of the story. We're in the middle of a chapter where the author has not yet decided where the plot is going. And we are reading along, taking notes, trying to understand the world we live in, knowing that the world we live in is bigger than our words for it, older than our timelines, and stranger than our equations have begun to predict. In the meantime, the telescope keeps gathering data. James Webb has not stopped. It is still up there, a million miles from Earth, drinking in photons from the deepest reaches of the cosmos. Every month, new observations arrive. Every month, the picture gets more detailed, and the puzzle gets more complicated. We are watching the universe rewrite itself in our notebooks. The cosmos is bigger than we thought. The cosmos is also older in some ways than we thought, younger in others. The cosmos is, by any honest accounting, exceeding the imagination of the people trying to describe it. So let us go back to the question, how big is the universe really? Let us try to give the most honest answer we can. The observable universe is 93 billion light-years across. We are reasonably confident about this number. It depends on the speed of light, the age of the universe, and the rate of expansion, all of which we have measured. The uncertainties on these measurements are small, on the order of a few percent. The observable universe contains approximately 2 trillion galaxies. This estimate has fluctuated over time as our surveys have improved. Earlier estimates put the number at around 100 billion, then 200 billion. Then, with the Hubble Deep Field and subsequent surveys, the number kept climbing. The latest estimates put it at around 2 trillion, though some recent reanalysis suggests this number might be too high. The true count may be somewhere between several hundred billion and a few trillion. The total mass energy content of the observable universe is roughly equivalent to 10 to the 53 kilograms. 5% of that is ordinary matter. 27% is dark matter. 68% is dark energy. The full universe, the part that exists but is not all observable, is at least 250 times larger by volume than the observable region. This is a conservative estimate, based on measurements of the curvature of space. The total universe might be 10 to the 23rd times larger than the observable region, depending on which model of inflation is correct. The total universe might be infinite. We cannot rule out infinite. We cannot rule it in either. The truth is that the size of the full universe is the kind of question we may never be able to answer definitively. The observable region is the only region we can directly measure. Everything beyond it is inference, and inference, however good, is not the same as observation. Beyond the question of the full universe, there is the question of the multiverse. If inflation happened, and the evidence suggests it did, then the framework that produced our universe almost certainly produced others, possibly an infinite number of them, each one isolated from every other by an infinite gulf of inflating space. Each one with its own physics, its own history, its own observers, if any. The multiverse, if it exists, is not a place we can travel to. It is not a place we can detect, except possibly through faint anomalies in the cosmic microwave background that might be the bruises left by ancient bubble collisions. The multiverse is the logical extension of the physics we trust. Its existence is implied by the equations. Its confirmation may be forever beyond us. So when we ask how big the universe is, we are really asking several different questions. How big is the part we can see? How big is the part that exists, but is invisible to us? How big is the structure of all reality, including other universes whose physics may not even match our own? The answers descend through layers of increasing speculation and increasing scale. And at every layer, the universe outruns the question. The observable universe is unimaginably large. The full universe dwarfs the observable region. The multiverse, if it exists, dwarfs the full universe. And there may be structures beyond the multiverse that we have not yet conceived. There is no obvious stopping point. There is no level at which the cosmos says, here, this is the whole thing, this is where it ends. Every level we have reached has revealed another level above it. Every map we have drawn has turned out to be a fragment of a larger map. The history of cosmology is the history of being humbled. Every century, we have learned that the universe is larger than the previous century thought. The ancient Greeks placed Earth at the center of a finite cosmos bounded by a sphere of fixed stars. Copernicus moved the Earth out of the center. Galileo found moons around other planets and stars in the Milky Way. Herschel mapped the structure of the Milky Way and suggested that the universe might be larger than anyone had imagined. Hubble proved that the Milky Way was one galaxy among many. The cosmic microwave background revealed that the universe had a beginning, a hot, dense moment from which everything emerged. The discovery of dark energy revealed that the universe is accelerating its expansion into an ever larger future. Inflation suggested that what we can see is one bubble in a vast inflating sea. At every step, the universe got bigger. At every step, we got smaller. At every step, the question of size revealed that the previous answer was a floor, not a ceiling. There is no reason to think this process is finished. There is every reason to think that the next century of cosmology will reveal that the universe is larger still, that the structures we have cataloged are details of a deeper geometry we have not yet seen, that the physics we trust is one expression of a more fundamental physics we have not yet discovered. We will keep extending the map. The map will keep growing. The universe will keep outpacing the cartographers. And on a small wet rock orbiting an average star in a minor arm of one galaxy among trillions in one bubble of an inflating, possibly infinite multiverse, we will keep asking, and keep finding that the answer is bigger than the question. There is something important about this process that should not be lost. The universe is humbling. The numbers are crushing. The implications are vertiginous. But the act of measuring those numbers, of running those calculations, of taking the universe apart and reassembling it in our equations, is one of the most extraordinary phenomena the cosmos has produced. Matter forged in dead stars, scattered across hundreds of millions of years of stellar wind and supernova, gathered into the cloud that formed our solar system, condensed into a small, wet, rocky world, evolved over billions of years into beings capable of looking up and asking how big it all is. The universe spent 13 billion years building an instrument that could measure itself. That instrument is us. Imperfect, brief, local, stuck inside one keyhole, unable to leave the room, and yet capable of inferring the existence of the building, capable of estimating its dimensions, capable of recognizing the difference between what we can see and what exists. That capacity is not nothing. That capacity is, in some sense, the only thing the universe has produced that knows what the universe is. The voids do not know they are empty. The filaments do not know they are bright. The galaxies do not know they are galaxies. We do. We are the universe's local mechanism for self-recognition. Briefly, improbably, in a moment of cosmic time so short it should not even register. And in that moment, we have managed to figure out that the cosmos is 93 billion light-years across at minimum, and probably much larger, and possibly infinite, and likely one bubble in an ocean of bubbles. We have figured this out from a planet so small that, photographed from Mars, it appears as a single pixel of light. From Saturn, it disappears entirely into the sun's glare. From the nearest star, it is unresolvable. From the edge of the galaxy, it is less than nothing, and yet from this nothing, we have measured everything we can reach. And we have understood, with growing humility, what we cannot reach. We can see 13 billion years into the past. We cannot see beyond the cosmic event horizon. We can model the first second after the Big Bang. We cannot model what came before. We can predict the heat death of the universe in 100 trillion years. We cannot reach 100 trillion years. We are visitors, brief visitors. We do not own the cosmos. We barely understand it. But we have looked. We have stared into the dark with patient instruments and demanded that the dark give up its secrets. And the dark has answered, one secret at a time, more secrets than we had imagined existed. The answer to how big the universe is not a single number. It is a process, a continuing dialogue between observers and a cosmos that always has more to reveal. The numbers we have are placeholders. They will be refined. They will probably be replaced. They will certainly be deepened by future measurements we have not yet conceived. But the question remains. The question is the engine. The question is what makes the journey worth taking, even when the destination is unreachable. So when someone asks you, how big is the universe really? You can answer like this. The part we can see is 93 billion light-years across and contains 2 trillion galaxies and 10 to the 24th stars. The part that exists is at least 250 times larger than that, possibly much more, possibly infinite. The part that is real, including any bubbles beyond our own, may have no boundary at all, and the part you can ever experience in any meaningful sense is the small patch of space and time that begins at your eyes and ends a few light minutes away, where the sun touches your skin and the moon waits in the dark, and the photons keep arriving, one after another, carrying news from places you will never visit. That is the answer. That is the cosmos. That is the size of the universe, really. And we are not done with the journey, because there is still the question of how the universe got this big in the first place. The story of inflation. The story of the first second. The story of how a region smaller than a proton became a cosmos larger than imagination in less time than it takes a photon to cross an atom. And there is the question of what the future holds. The far future. The far, far future. The future so distant that the words we use to talk about time begin to lose their meaning. There is the question of whether anything we have built, anything we have learned, anything we are, will leave any trace at all in the cosmos as it ages into its long, cold, empty maturity. And there is the question we keep returning to, the question that the size of the universe makes impossible to ignore, the question of whether we are the only beings asking. We have to talk about that question. We have to follow the evidence as far as it will lead. We have to look at the silence of the cosmos and ask what the silence means. Because the universe is full of voices, or empty of them, and either possibility carries weight that should keep us up at night. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation drifted to the question of extraterrestrial life. Fermi, known for his ability to perform rough calculations in his head with extraordinary speed, considered the numbers. The age of the galaxy, the number of stars, the likelihood of planets around those stars, the time required for a technologically capable civilization to spread across the Milky Way, even at modest speeds. And he reached a simple, devastating conclusion. If intelligent life is common, the galaxy should be filled with evidence of it by now. Civilizations have had billions of years to arise and spread. Even at speeds far below the speed of light, a single technological civilization could colonize the entire galaxy in a few tens of millions of years. A blink in cosmic time, and yet there is no evidence that anyone has done so. No confirmed signal, no visitation, no artifact, no megastructure visible to our instruments, nothing. Where is everybody? That question, the Fermi paradox, has only gotten heavier with time. Our telescopes have grown more powerful. Our surveys have expanded. We have listened for radio signals across millions of frequencies. We have scanned the skies for laser pulses, infrared signatures, gravitational anomalies. We have looked at hundreds of thousands of stars, with instruments sensitive enough to detect transmissions from civilizations, using technology not much more advanced than ours. We have found nothing. The galaxy, by every measurement we can make, is silent. And the silence is the cleanest data we have. The numbers, taken together, should be overwhelming. The Milky Way contains 400 billion stars. Recent estimates suggest there may be more habitable zone planets than stars, somewhere between 300 million and 10 billion potentially life-friendly worlds in our galaxy alone. Scale that to the observable universe and the number of potentially habitable worlds runs into the billions of trillions. The probability that life is unique to Earth, that we are the only place in all of that where chemistry crossed the threshold into biology, seems vanishingly small, unless something is missing from our picture. Unless there is a step somewhere in the chain, from dead chemistry to a galaxy-spanning civilization that is far harder than we have any reason to believe. The economist Robin Hanson called this hypothetical barrier the Great Filter. It might lie behind us. It might lie ahead. If it lies behind us, in the origin of life, or in the leap from simple cells to complex ones, or in the emergence of intelligence, then we are extraordinarily rare. The galaxy is full of dead worlds because almost nothing makes it past the early steps. We are among the lucky few. The silence means we are alone, and our existence is precious beyond measure. If the filter lies ahead, the implication is darker. It means civilizations arise routinely, develop technology, and then fail. Some barrier, built into the structure of intelligence or technology or biology, eliminates them before they can leave a lasting mark on the cosmos. We are entering that barrier now. We are inside it. The window during which a civilization is powerful enough to broadcast its existence, and not yet wise enough to ensure its own survival, may be too narrow for most species to pass through. The galaxy may be littered with the chemical traces of dead civilizations, ruins so old and so erased by geological and astronomical processes that no signal of their existence remains. We do not know which version of the Great Filter is correct. We may not know in time to do anything about it. But the architecture of the cosmos itself offers another possible answer. One that requires no filter at all. One that the size and structure of the universe alone may explain. The universe may be too large for anyone to find anyone else. The voids stretch hundreds of millions of light years. The filaments where galaxies cluster are thin and far apart. The cosmic event horizon seals off the majority of the cosmos permanently. Within our own galaxy, the distance between stars averages around 4 light years. A signal sent from one civilization to another might take centuries to arrive. A response might take centuries more. By the time a conversation completes a single exchange, the civilizations involved may have transformed beyond recognition or vanished entirely. And across intergalactic distances, the problem becomes worse. Andromeda is 2.5 million light-years away. The Virgo cluster is 54 million light-years away. A message sent to a civilization in the Virgo cluster today would arrive 54 million years from now. Whatever sent it would almost certainly be gone. Whatever received it would have no way to send a reply that could ever reach the original sender. The universe is structured to keep its inhabitants apart. The expansion of space carries galaxies away from each other faster than light can cross between them in many cases. The cosmic event horizon shrinks the volume from which we could ever receive a signal. As time passes, the horizon closes in further. More galaxies cross beyond reach. The fraction of the universe with which any single civilization could in principle communicate decreases with every passing eon. We are alone not necessarily because no one else exists. We may be alone because the architecture of the cosmos makes togetherness impossible across the distances involved. The universe is big enough to contain countless civilizations and isolated enough to prevent any of them from finding any others. This is perhaps the most poignant answer to the Fermi paradox. Not silence because of emptiness, silence because of distance. Silence because the cosmos is structured in such a way that its inhabitants are forever quarantined from each other. Voices calling out into oceans too vast for any voice to cross. The night sky may be full. The night sky may also be silent. Both can be true at once. And what does this mean for us? It means we live on an island. A small wet island, orbiting a moderate star, embedded in a minor arm of one galaxy among trillions. We have evolved on this island, developed civilization on this island, built instruments capable of measuring the broader cosmos from this island. And we may live on this island forever. Not because we cannot leave Earth. We can. We will. We will probably reach Mars within this century. We will probably reach the outer solar system within the next. We may eventually send probes to other star systems, traveling for centuries or millennia to arrive at worlds whose details we currently can only guess at. But the cosmos beyond our local stellar neighborhood, beyond a few thousand light years, may remain forever out of reach. We can see it, we cannot touch it, we can study it, we cannot visit it. We can wonder about its inhabitants, if any. We cannot meet them. This is the price of the size of the universe, the price of living in a cosmos this large, the cost of being one fragment of one bubble in an inflating multiverse. And yet, here we are. The size of the universe does not erase us. The silence of the cosmos does not diminish us. The isolation built into the structure of space does not strip our existence of meaning. We exist. We measure. We understand. We ask. We pass our wonder down the generations through language and image and equation. We have done in 3 centuries of modern science what no other species we know of has ever done. We have figured out our address in the cosmos to a precision that allows us to estimate its dimensions, calculate its age, infer its origin, and predict its fate. That is extraordinary. That is, in a strange way, the most extraordinary thing in the cosmos. The universe spent 13 billion years building structures, organizing matter, scattering stars across galaxies, weaving the cosmic web. And on one small planet, that matter looked back. The voids do not know they are empty. The filaments do not know they are bright. The galaxies do not know they are galaxies. We do. Every atom in your body was forged in a star. The iron in your blood was synthesized in a supernova. The calcium in your bones was assembled in the final convulsions of stars that died before our sun was born. The hydrogen in the water that fills your cells has existed since the first 3 minutes after the Big Bang. You are not separate from the cosmos. You are the cosmos, a specific arrangement of cosmic matter that has developed the capacity to contemplate itself. Hydrogen, given 13.8 billion years, became something that could wonder about hydrogen. That is not insignificance. That is the climax of the story. That is the moment toward which 13 billion years of cosmic evolution has been moving. Not because the universe had a goal. The universe has no goals. But because in a cosmos large enough and complex enough, given enough time and the right initial conditions, matter can sometimes organize itself into observers. And we are the observers. Briefly, fragilely, in a moment so short on cosmic timescales that the universe has barely had time to notice. But we are here. And we know. We know the universe is at least 93 billion light-years across, and probably vastly larger. We know it is filled with 2 trillion galaxies and 100 septillion stars. We know it is composed mostly of substances we cannot see and forces we cannot explain. We know it is expanding. We know that expansion is accelerating. We know that expansion will eventually carry most of the cosmos beyond any signal we could send. We know we are running out of time, in some sense, to learn what we still want to learn. And we keep learning anyway. We keep building bigger telescopes. We keep proposing new theories. We keep arguing about whether the standard model needs revision or refinement or replacement. We keep doing the work. Because that is what observers do. The universe is large beyond imagination. The universe is also, briefly, ours. The matter we are made of, the light that reaches our eyes, the patterns of the cosmic web visible in our telescopes, the photons of the cosmic microwave background still arriving at our detectors after 13 billion years of unbroken travel. All of it belongs to us in this moment. Not in the sense of ownership. The cosmos does not belong to anyone. But in the sense of relationship. We are in relationship with the cosmos. We are part of it. We are made of it. We see it. We carry its history in our atoms and its laws in our equations. And when we finish asking how big the universe really is, we are left with an answer that does not fit in a number. The universe is large enough to humble us. The universe is intricate enough to fascinate us. The universe is mysterious enough to keep us asking forever. And the universe is, against all probability, capable of producing instruments that can measure it. We are those instruments. Imperfect, local, brief, inside one keyhole, unable to leave the room, but somehow still capable of inferring the building, still capable of estimating its dimensions, still capable of recognizing the difference between what we see and what is. The answer to the question is that the universe is bigger than the question, larger than every framework we have built to describe it, older than every story we have told about its origins, stranger than every model we have constructed to predict its behavior. And we, knowing all of this, still keep looking, still keep measuring, still keep asking. Because the question is the engine. Because the cosmos is worth understanding even when full understanding is impossible. Because the journey, in the end, may matter more than any destination we could ever reach. Look up tonight. Find a dark place if you can. Let your eyes adjust to the night. Look at the band of the Milky Way stretching across the sky. Pick out a faint patch of light that might be Andromeda. Find a constellation you recognize. Locate a planet if any are visible. Watch the stars wheel slowly overhead as the Earth turns beneath you. And remember what you have learned. Remember that every star you can see is in your immediate neighborhood. That the band of the Milky Way is the inside of your own galaxy seen edge on. That Andromeda is 2.5 million light-years away, and its light left it before our species existed. That beyond Andromeda are hundreds of billions of other galaxies, stretching out to a horizon 93 billion light-years across. That beyond that horizon is more cosmos, at least 250 times larger by volume, possibly far more, possibly infinite. That beyond all of that may be other bubble universes inflating in a multiverse without end. Remember that you are standing on a small wet rock at the bottom of a thin layer of air, looking at a sky that contains more than you can ever know. Remember that the light reaching your eyes has traveled distances and times that defy intuition. Remember that the matter in your body was scattered across the cosmos before it gathered itself into you. Remember that you are a configuration of cosmic material that has somehow learned to ask how big the cosmos is. And remember that the answer, when you follow it as far as you can, leads not to a number but to a kind of awe. The universe is bigger than imagination. It is bigger than measurement. It is bigger than the brains it has produced. It is bigger than the species that builds the telescopes to study it. It is bigger than the entire civilization that has spent the last few centuries trying to map it. And we, knowing this, do not despair. We do not turn away. We do not pretend that the question is too large to ask. We ask. We keep asking. We will probably keep asking for as long as we exist. And our existence in a cosmos this large is itself the most improbable and the most precious thing we will ever encounter. Be small. Be local. Be brief. Be one configuration of matter among countless others. And be the one that asks. That is what we are. That is what we have been doing for thousands of years. That is what we will keep doing for as long as anyone is here to do it. The universe is big. The universe is also, briefly, watching itself through your eyes. Both are true. Hold them both. Carry them with you out of this moment and into the rest of your night. The stars will be there tomorrow. The galaxies beyond them. The cosmic web beyond those. The horizons. The voids. The dark scaffold. The mysterious energy stretching everything apart. All of it will be there. Waiting. Indifferent. And patient. And we will keep looking. If you have made it this far with us, thank you. Thank you for sitting with these enormous questions. Thank you for letting your mind stretch toward scales it was never designed to hold. If you found something in this journey that made you stop and feel small in the right way, leave a like on the video and subscribe to Hidden Beyond Stars. It helps more than you know, and it lets us keep building these documentaries for people who, like you, look up and wonder. Tell us in the comments what surprised you most. Tell us which scale broke your imagination first. Tell us what you want us to explore next. The cosmos is full of questions. We will keep walking toward them, one episode at a time, for as long as there are people willing to walk with us. Take care of yourselves. Take care of each other. The universe is large. We are small. But we are here. And that is enough. We will see you in the next investigation.